Welcome back to Calculus 2. In this lecture, we're going to introduce one of our first tests determining when an infinite series converges or diverges. All right, let's go back to the beginning when we first gave our definition of what it meant for an infinite series to converge or diverge. And that was based off of looking at the sequence of partial sums and its limit. This is in general very difficult. You have to go from the terms of an infinite series into a sequence of partial sums and hope you can find a formula for the expression for S sub n. This is highly inefficient. Most examples, that's going to be extremely difficult or impossible to find a formula for the sequence of partial sums. So what we're going to try to do from here through the next few topics in the course is come up with some shortcuts or tests for determining when an infinite series converges or diverges. All right, let's take a look at two examples to kind of motivate some ideas for what these tests might tell us. The first example we're going to look at is the infinite series where the general term is given just by n. And if we start with our index value for n as 1, what we get here is the infinite series 1 plus 2 plus 3 plus 4 plus 5. Now we saw earlier that we can, in this case, find a formula for S sub n. And that gave us an idea that this was divergent. Now, an intuitive or basic way to look at this is that the terms A sub n are getting bigger as we go further in that infinite series. And if you think about it, adding up terms that get increasingly bigger, the end result should be a very large sum. If you add up an infinite amount of increasingly larger terms, your end result should be that you get an infinite sum. So thinking about this a little bit differently, although we have to be careful with our intuition when dealing with infinities in mathematics, especially infinite series, we do see here that as A sub n gets bigger, the sequence of partial sums gets bigger, leading us to conclude that this infinite series diverges. All right, that one seems pretty straightforward. It's what you would expect. 1 plus 2 plus 3 plus 4 plus 5 forever should get bigger. All right, let's introduce a very important infinite series, one called the harmonic series. The general term is given by A sub n equals 1 over n. And if we start the index with 1, we get not the natural numbers like above 1, 2, 3, 4, and 5, but 1 over n, we get the reciprocals of the natural numbers. The name harmonic series comes from how the ancient Greeks were looking at these ratios. If you have any familiarity with music, there's various intervals called maybe a third, a perfect fifth, so on and so on. And this is where the name harmonic comes from, borrowing terms from music. Now, the terms here, 1, a half, a third, a fourth, and a fifth, those actually get smaller, unlike the example above where the terms for A sub n get increasingly bigger. Now, this is a very counterintuitive infinite series. Even though the terms do get smaller, this is actually divergent. In other words, the harmonic series is a divergent infinite series. One way to see this, which we're not going to go into detail about, is if you were to look at the sequence of partial sums in this case, trying to find a formula for S sub n is difficult, but what you can show or prove is that the term S sub n is always greater than 1 plus n over 2 in the case where n is even. And what this says is as you look at higher terms in the sequence of partial sums, they're all getting bigger. Since 1 plus n over 2, that gets bigger as n gets bigger. So what this basically says is that your sequence of partial sums, S sub n, each term gets bigger. The limit of that is going to approach infinity for S sub n as n goes to infinity. And since the limit of the sequence of partial sums doesn't exist, it's infinite, we find that our infinite series diverges. And this is, again, highly counterintuitive since the terms do get smaller. This is going to play a central role in a lot of the ideas we'll be seeing throughout the rest of the course relating to infinite series. So always keep the harmonic series in mind, especially throughout the rest of this lecture. All right, before we get to one of our first tests called the divergence test, let's take a look at what those examples tell us. And what we can extract from those two is that if we have an infinite series and we want it to converge, we have to have that the terms a sub n approach 0 as n approaches infinity. So we would say that the limit of a sub n, the general term, has to equal 0. All right, if you think about the harmonic series, that by itself, that the terms approaching 0, that is not sufficient to guarantee that the infinite series converges. The harmonic series is a great example. The terms a sub n as 1 over n do approach 0. However, the harmonic series diverges. Again, that's highly counterintuitive. All right, this brings us to kind of our first theorem, which we kind of have stated above, but we're going to make it official. The theorem states that if we have a convergent infinite series, then the limit of the term has to be 0. All right, we're going to look at this through the lens of mathematics. Theorems or statements in mathematics always take the form of if conditions are met, then you reach a conclusion. And here, the conditions, what we're going to call P, follow the if part. The conditions here are if we have a convergent infinite series or if the infinite series converges. For this theorem, the conclusion, Q, is that the limit of a sub n equals 0. All right, before we get into what follows, let's take a look at a general statement, or what's called in logic an implication, which takes the form if conditions P are satisfied, then you reach the conclusion Q, or if P, then Q. Let's think of a basic example, which you can see to the right there. The basic statement or implication we're going to consider is as follows: if you're at Mercer County Community College, then you're in New Jersey. And that certainly is true. All right, to lead into what the divergence test is, let's introduce what's called the converse of a statement or implication. And this switches the conclusion with the conditions. So if our statement has the form P implies Q, the converse switches that, Q implies P. If we think about that with respect to our basic example, we reach the following: if you're in New Jersey, then you're at Mercer County Community College. And that is false. You could be elsewhere in the state of New Jersey, but not at Mercer County Community College. So in general, for a statement, P implies Q, its converse is false in general. All right, and if we take a look at the theorem above, the theorem being if the infinite series converges, then the limit of the term is 0. Let's take a look at the converse of that. The converse of that theorem would say if the limit of the term equals 0, then the infinite series converges. Now keep in mind the harmonic series, that would be what's called in mathematics a counterexample to this converse. So in mathematics, all it takes is one example, what's called a counterexample, to prove that statement false in general. The harmonic series, the term a sub n as 1 over n, that does approach 0. However, the harmonic series is a divergent infinite series. Again, that's highly counterintuitive. All right, now the converse is in general false for a statement, but what is true or logically equivalent to our implication P implies Q is this other quantity or expression called the contrapositive, which basically switches the conditions and conclusion, but at the same time negates them. So our contrapositive would be if not Q, then not P, or not Q implies not P. Now, what does that mean for our basic example? The example being, if you're at Mercer County Community College, then you're in New Jersey. The contrapositive of that would be as follows. If you're not in New Jersey, then you're not at Mercer County Community College. And that is true. It's logically equivalent to our basic statement or implication, P implies Q. Now let's again go back to our theorem stated here, the theorem being if the infinite series converges, then the limit of the term equals 0. Let's take a look at the contrapositive of that theorem. All right, the theorem stated there, if we switch the conditions with the conclusion while at the same time negating them, we get this statement, what we're going to call the divergence test. Now let's just think about for a moment what negating these would mean. Let's say we have the limit of a sub n equals 0. Negating that would say the limit then is not 0. And if we look at the conditions there, if the infinite series converges, what would not converging mean? Then the infinite series would diverge if it's not converging. So if we switch the conditions and conclusion while negating them, we get this statement. If the limit of the term is not 0, then the infinite series diverges. And this is what we call the divergence test. Let's take a look at some examples. This is a really quick, nice test to apply to an infinite series to determine if it converges or diverges. We're going to see that in some following examples. So let's say for our first example, where the term a sub n is given by n divided by 2n plus 1. What the divergence test wants us to look at is the limit of the term. All right, if we take the limit of that term, the limit as n approaches infinity, you could here use L'Hopital's rule if you want, or just think back to some simpler results from Calc 1. The degrees of the powers of n are equal, so the limit here would be the ratio of those leading coefficients of that highest power of n. Or again, you could apply L'Hopital's rule. Either way, you'll find this term approaches the limit value of 1/2. And since 1/2 is not 0, the divergence test tells us then that the infinite series with that term is divergent. Again, really quick to apply, just look at the limit of your term, and if you get the limit as anything other than 0, your infinite series diverges. All right, let's take a look at a second example here. The term is given now by e to the 1 over n. This one requires maybe a little more thinking in evaluating the limit. All right, if we were to take the limit as n approaches infinity, an earlier result that we introduced on sequences is that when you have a continuous function like e to the x, you can bring the limit inside of that. So if we bring the limit inside the exponential function, that puts the limit up into the exponent, since that's where the input for exponential functions are. We end up looking at the limit of 1 over n as n approaches infinity. And that limit of 1 over n, that becomes 0 as n approaches infinity. So what we find here is the limit of our term approaches e to the 0. E to the 0, anything to the 0 power is 1, which is again not 0. The divergence test would tell us this infinite series diverges. All right, and that basically ends our first test here, the divergence test. As we continue with other lectures, we'll see other tests that are maybe a little more complicated to apply for determining when an infinite series converges or diverges.